Welcome. Good afternoon, everyone. My name is Divine. I'm the communications coordinator for our introduction number. So welcome to our Lunch and Learn session. So today our Lunch and Learn topic is quantitative evidence synthesis, why we do it and what methods are available. Our guest speaker for today is Professor Laura Bojke, who is the Professor of Health and Economics and Yorkshire ARC Team Lead for Health Economics and based at Center for Health Economics at University of York. So just to let you know that this session is recorded, and this recording will be added to our YouTube channel at the end of the week, and we're also sending out links to the recording. If you could ensure that everyone and you mute yourself, please, that will be great. And we'll have a time for questions at the end of the presentation. So I'll hand over to this to Professor Laura now.
That's great. Thank you very much. So I'm just going to share my slides. Hopefully that all goes okay. Okay. If any of my colleagues let me know if there's any problems with that. Otherwise, I'll assume we're okay to go. Okay. So welcome everyone to this session. It's going to focus on quantitative evidence synthesis, so I hope that's what you're expecting. I'm going to talk about the rationale for evidence synthesis, how we conduct it, and how to interpret the results. So just a disclaimer, as Divine said, I am a health economist, so this is from a health economics perspective. I'm not a statistician, so if you do want to delve further into more complex methods, such as I'll kind of get to at the end of the presentation, I'd advise exploring resources such as the Decision Support Unit documents at the University of Sheffield, and there are also a number of specific courses on evidence synthesis as well, including those offered at the University of Bristol. So with that caveat, we'll forge ahead. So in terms of specific content, I'll primarily talk about meta-analysis, but I'll also cover extensions of this, such as meta-regression and network meta-analysis. And then I'll briefly touch on, as I said, more complex methods such as match-adjusted indirect analysis as well. So why do we conduct quantitative evidence synthesis? So the combination of data from multiple sources primarily allows us to reflect all of the available evidence rather than being selective for single inputs, for example, to inform effectiveness or cost effectiveness in conclusions. It also enables us to increase our power to detect differences by expanding the size of our evidence base. And this in turn allows us to explore any heterogeneity in our effect estimates and therefore identify if there are particular subgroups where there may be differences in treatment effects, for example. Now, you could argue that primarily for decision-making contexts, it could be quite challenging if we were to present them with single sources of data, and this may involve retesting with alternative data sources. And so these summaries allow us to enable decision makers to reach conclusions about research questions of interest, and they also crucially provide inputs into cost effectiveness analyses as well. So evidence synthesis can be useful and a powerful tool, but there are some requirements of evidence synthesis. I guess a kind of bare minimum set of requirements to ensure its usability and its applicability to help inform those questions that I mentioned previously. So first, in terms of the methods that it uses, overall, it should be explicit and transparent in those methods. And in particular, it should be very clear about how the studies that are part of the quantitative evidence synthesis were identified, how those that were relevant for the synthesis were selected, how those were deemed were not relevant, were excluded, and then very clear about the methods that are used for pooling. And in particular, how between study heterogeneity is reflected and how within study uncertainty is reflected as well. And I'll go on to some of these issues in subsequent slides. So hopefully this will become clear. Now, evidence synthesis, when it's conducted well, constitutes some of the best forms of evidence. Systematic reviews are considered the strongest and highest quality evidence in terms of this evidence hierarchy. And meta-analysis specifically links to systematic review by generating a statistical summary of effect estimates across multiple different studies. And it's also considered a high quality form of evidence. So where does meta-analysis fit in terms of the entirety of the evidence base relating to a particular question? So here we can think about a particular question might be the relative treatment effect for a treatment X compared to another treatment, and it's for a particular condition Y. Okay, so the totality of all that available evidence, we can think of that as everything within that blue circle. And that includes non-experimental evidence, observational studies, information that may be identified from the grey literature, for example. And a much smaller selection of studies would be suitable for a systematic review, which would typically just focus on RCT evidence. And that would be reflected within this kind of orange circle. And then an even smaller subset we could actually utilize within meta-analysis. So specifically, meta-analysis requires empirical studies, so it requires quantitative studies, and they need to be reported in enough detail to permit us to retrieve sufficient information about those treatment effects. And I'll go on to specifically what that means in terms of the variables of interest in a little bit. But just to illustrate here that it's a much smaller subset of the entirety of available evidence that we actually include meta-analysis. And that's very important in terms of then relaying this to decision makers. It's only a small part of that entirety of evidence, and therefore it just forms a part of a decision-making process. So before we go on to what is needed to inform a meta-analysis, what exactly is a meta-analysis? Okay, so it's been defined as a statistical method of quantitatively combining results from multiple studies to reveal the nature of the relationships that exist amongst relevant variables. So ultimately, a meta-analysis aims to quantify effect sizes and their uncertainty as well. In practice, meta-analysis simply pools estimates of relative effect measures across studies, but also considers between and within study variability as well. Okay, and the ways in which it does that, I'll go on to in a little bit, and I'll illustrate that with examples as well. So what information is needed to inform meta-analysis? So I'm going to talk here about relative treatment effect measures primarily. However, the kind of same principles apply for other measures such as costs or health-related quality of life, although the measurement scales may be somewhat different. So for each study, we need to be able to extract, usually from published information, summaries that enable us to calculate two key things. The first being a central or point estimate of that treatment effect, and that would usually be a mean. In some circumstances, it may be appropriate to report a median, but usually that would be a mean. And then some measure of uncertainty. That would typically be a standard error around that estimate of the mean. Just to note here that in terms of information reported, many relative effect measures tend to be ratios, and I'll go on to describe those. And so often what you might see when you see results from meta-analysis is things reported on the log scale. And that'll often happen before pooling. And that's because some of those ratios tend to be quite skewed. So for example, when we're dealing with odds ratios, those tend to be skewed. And so there's often a lot of transformation that happens. So you'll often see that reported. So aside from that information that you might require when we're dealing with aggregate level data, if we are dealing with individual patient data meta-analysis, and I'll briefly describe that towards the end of the presentation, that obviously requires access to the raw data, so would require patient level information on whether or not events occurred for particular patients, or perhaps the timing of those events as well. So in terms of relative effect measures, the important distinction when determining which specific measure is this distinction between whether or not it's binary data or continuous data. So for binary outcomes, what I mean there is either the presence of an event or not having an event. So that could be death or survival. An individual either has an event or they don't have the event. And for binary outcomes, that the most commonly used measure is something called relative risk. And the relative risk is the ratio of the probability of an event occurring with an exposure, so that's having the intervention, versus the probability of the event occurring without the exposure. So that would be for the comparator group. Next, some studies may report odds ratios, which you'll often see in the clinical literature. And the odds ratios are the odds that the outcome will occur given a particular exposure. So again, that could be the treatment compared to the odds of the outcome occurring in the absence of that exposure. And in a bit, I'll go through how those exactly how those calculated from those binary outcome data. Alternatively, for binary outcomes, we could present a risk difference. So that's not a ratio, that's just a difference in those risks between those alternative studies. Again, for individuals that have the outcome of interest versus those that don't. So for continuous outcomes, and this may include things such as changes in BMI, changes in blood pressure, we can compute the average absolute difference between groups. So again, that would be the exposed group versus the not exposed. And this can give so for example, if these are divided by a measure of variation in that study, usually standard deviation, this gives us a better way of combining effect estimates from different studies. So that would be a kind of common way to deal with continuous data. There are two kind of alternatives that don't kind of neatly fit into continuous or binary data. One being rate ratios, and these are very closely related to risk ratios, but they're computed as the ratio of the incidence rate in an exposed group divided by the incidence rate in the unexposed group. And then typically for things like time to event data, we would compute something called a hazard ratio. And the hazard ratio is a measure that's often used in survival analysis. You'll see that, and it's the rate at which an event occurs. So again, that could be related to survival data. It's the rate at which individuals within a particular group would be dying over time. And a ratio can be calculated by comparing those two groups. So those are the kind of typical types of measures that we might see in meta-analysis. So this may seem a little bit abstract and perhaps a little bit kind of confusing. So this is an example using probably the more kind of simplistic outcome, which is a binary outcome. And this is a meta-analysis of RCTs looking at the effects of aspirin on deaths. So that's our outcome of interest. Individuals within these studies die or don't die. And this is following the use of aspirin following a heart attack. So we can see in this table here, we've got 7 studies, all of which have a treatment and a comparator arm, and we observe outcomes within these studies. As you can see, these studies are of different sizes. We've got some very large studies, we've got some quite small studies, we've got different numbers of events. So that's the kind of starting point for thinking about synthesizing this data from all these different studies. So before we synthesize information across these studies, we first need to calculate those relative effect measures for each of the individual studies. So here we choose to calculate the odds ratio, and we can see how this is calculated using the 2x2 table of events for a single study. So here I've just categorized it as A, B, C, D, just to make it a little bit clearer about what information is needed in each of those steps. So we can calculate the odds ratio using that the event and the no event data from the treatment and the control arms of the studies. We can also express the uncertainty around this relative effect measure, and here we calculate the 95% confidence intervals. And as I mentioned, odds ratios in particular tend to be quite skewed. So we calculate this measure of uncertainty by first logging the odds ratio. As I said, they tend to be quite skewed and therefore mathematically quite challenging to deal with. So what we have here is 95% confidence intervals for the log of the odds ratios. So relatively straightforward. That can be done, in a matter of minutes within Excel, just kind of plugging those numbers in to calculate those relative effect measure and also the uncertainty for that relative effect measure for that one individual study. And we can do that for each of those 7 studies that we have identified as potentially relevant in terms of informing a question about the effectiveness of aspirin given to patients after they've had a heart attack in terms of reducing the likelihood of them dying. So we calculate the odds ratio across each of those 7 studies, and this forest plot just shows those odds ratios for each of those 7 studies. So here we can kind of visually see the differences where studies have larger confidence intervals. Those may be smaller studies, so we're more uncertain about that effect estimate. So it kind of provides a useful visual representation, but ultimately doesn't enable us to then produce a summary. Okay, so what if we want to summarize across each of those 7 studies to say something about the totality of the evidence and what it demonstrates in terms of the relative effect of aspirin in reducing mortality in this population? So to estimate an overall effect for aspirin in reducing mortality, we want to reflect the size of the studies that inform that overall or that mean estimate. So what I mean there is it needs to be a weighted mean effect. Okay. So we can generally there use 2 different approaches, and these are referred to as either fixed or a random effects model. So the 2 make different assumptions about the nature of the studies, and these assumptions lead to different definitions for the combined effect and different mechanisms for assigning those weights to individual studies. So first, under the fixed effects model, crucially, we assume that there is one true effect size that we are trying to estimate, and that's shared by all of those included studies. So each of those 7 studies are attempting to estimate one true effect. And therefore, it follows that the combined effect is the estimate of this common effect size. So if we just start to populate this slide here, we can see that the result arrow is pointing to the result for an individual trial, okay? And therefore, any deviation between that result and the true effect, okay, is the random error, okay? That's just sampling uncertainty because every study within that pool of 7 is trying to estimate one true effect size, okay? And we can see we can populate with alternative trials, but they're all trying to estimate that one true effect. And that's the kind of crucial component of a fixed effect model. The only source of error within our estimate of the combined effect is that random error within studies. Okay. That therefore means that with a large enough sample size, the error will tend towards 0. It will eventually asymptote to 0. Okay. So this holds true whether or not the large sample size is confined to a single study or distributed across many studies. The more information that we get, okay, that random error disappears, okay, and that's the kind of assumption of the fixed effects model. So what if we start to next in terms of weighting, so under the fixed effects model, all studies are, as I said, estimating the same effect size. So we can assign weights to the studies based entirely on the amount of information that's captured by that study. And here we're talking about the sample size here. So a large study would be given the lion's share of the weight, and a small study would be largely ignored in the pooled estimate. And the inverse variance method is the most commonly used way to calculate these weights, and it's roughly proportional to sample size, but it's slightly more nuanced, and it attempts to minimize the variance of a combined effect. So here in this slide, VI is the within study variance for a particular study I, and then the weighted mean is the sum of the effect sizes multiplied by the weight for that particular study. Okay, and then the variance of the combined effect is defined as the reciprocal of the sum of all of those weights. Okay, so these are things that can be quite easily kind of pulled out of standard statistical software, or indeed these can be calculated in things like Excel using relatively kind of simple formula. So here I've just presented the fixed effects results in terms of that forest plot. So again, we've got those odds ratios and their 95% confidence intervals from the individual studies. But you can see here now we've got that diamond shape at the end of the forest plot, and that represents that pooled estimate using a fixed effects model. So we can see where that's kind of positioned in terms of the forest plot, that it's largely taking a lot of that combined weight from this very large study, ISIS-2. Okay, so a lot of that mean is coming from that large study in which there isn't much uncertainty, okay, because it's got a large sample size. It's been drawn slightly in, but predominantly follows the findings from the ISIS-2 study. And as I said, these are very easy to do in Excel. There are other software, particularly if you're thinking about generating forest plots. Excel can be quite clunky in that regard, but standard statistical software can enable you to produce these results. Now, as I said, the fixed effects model assumes that all of those trials, all those 7 studies are estimating the same underlying treatment effect. So the next step in terms of meta-analysis is to determine if that is a reasonable assumption. And there may be a rationale for further exploration. It may be that we believe that the trials are different in design and conduct, or maybe in terms of the characteristics of the patients or the intervention. So that could be including the dose of the drug. So we may want to kind of probe further into that. We can conduct statistical tests to determine if there is a level of heterogeneity, and I've just put 2 of the most commonly used tests for heterogeneity here. Cochrane's Q test, also referred to as the chi-squared test, or the Higgins I-squared. Again, these are things that you can quite easily calculate in Excel or plop out of software such as Stata. So relatively easy to calculate that. It will tell you how much of the variability is due to heterogeneity. Okay, there's then an issue around interpretation, but generally, the kind of larger the score, the more significant the heterogeneity is in terms of your pooling. So what do we do next? If we believe or have determined from statistical tests that heterogeneity exists, we can move to a random effects model. So in a random effects model, rather than assume that there is one true treatment effect, as we had with the fixed effects model, we can reflect the fact that there is a distribution of true effect sizes, which you can see here by this kind of blue distribution shape on the slide. And therefore, the combined effect cannot just represent one common effect, but instead it represents the mean of the population of true effects. So it's the mean of that distribution of individual study level treatment effects that have been estimated. So it's incorporating much that variability that we might think is perfectly reasonable between individual studies because perhaps we have different patient characteristics, the trial has a different dose for the medication, etc. And so we wouldn't expect everything to tend towards one common effect. And a random effect allows you to integrate that heterogeneity. So you may also then within trials have a degree of random error, because when you conduct a trial, you determine the effect estimate usually with absolute certainty. So you still have that sampling uncertainty from those individual studies, but each individual study is estimating a trial specific effect, and it is the mean of those trial specific effects that determines your overall combined effect. Okay. And I'm just putting in here just those individual trial effects and the random errors associated again with the individual trials. Okay, so how do we then calculate weights in a random effects model? So the key thing here is we need to take account of two sources of error and two levels of sampling. Okay, so first, the true effect sizes are distributed about a particular mean with a variance. Okay, and this reflects the actual distribution of true effects around their mean. Okay, so first we need to reflect that, and second, the observed effect for any given trial will have some distribution as well. Okay, so we need to take account of that between study differences and within study that we've got that sampling uncertainty as well. So we need to deal with that in terms of assigning weights for individual studies. And we can again use the inverse variance weighted approach, and that's commonly used in random effects. But here, the key thing is that it adjusts the weights, okay, using an estimate of the amount of heterogeneity, and we call this tau squared, okay. So it adjusts those individual weights that then reflects how much heterogeneity is between those individual studies. Again, this is information that can be plopped out of, we can calculate it from Excel, we can calculate tau squared, and we can also calculate it from standard statistical software such as Stata. Okay. I've plopped in the results there from the random effects estimate at the bottom of that forest plot. So you can see here that we've got a much flatter diamond. And there is a reason for that, and I'll go on to that in the next slide. But again, we're able to estimate a single effect across each of those studies, but it tries to reflect the fact that each of those 7 studies is slightly different, maybe in terms of characteristics, etc. So it's trying to incorporate some of those things as well. So the random effects allows for heterogeneity. It statistically includes it by estimating that tau squared parameter, but it doesn't explain it. Okay, the explanation needs to happen on a qualitative basis. Okay, it can only incorporate what it can observe statistically. Okay, it is certainly the case that when there are few studies, so for example, if we had 2 or 3 studies, it would be quite difficult to estimate that tau squared. It is likely that the tau squared would demonstrate that there is little or no heterogeneity, when actually we may believe that there is. It's just that we've got a much more limited sample of studies. And in those circumstances, you would find that the fixed and the random effects would give you pretty much the same results. And so, but it's not the case that there isn't heterogeneity. We just haven't got sufficient studies to be able to estimate it in a robust way. In terms of what we get back from the random effects, as I said, you saw a much flatter diamond at the bottom of that the forest plots, and that's the case because the inclusion of that heterogeneity changes the weights. As I said, we integrate that tau squared parameter, so we tend to get much wider confidence intervals for the pooled effects. Smaller studies get relatively larger weights compared to the fixed effects. So previously with the fixed effects model, it was all about the sample size. So if you remember back to the forest plot, it was primarily about the one study, ISIS-2, that had a large sample size that gave us our summary mean of our relative treatment effect. The mean is much more drawn in from some of the smaller studies when we use the random effects model. So you do get some differences. Okay, so that's fixed versus random effects. Probably lots of detail there in terms of the kind of technical exposition, but hopefully I haven't scared you too much in terms of how you'd conduct that. Honestly, it can be a few lines of code in Stata or relatively simple functions to incorporate within Excel. As I said, a random effects model cannot explain heterogeneity, and so there is a real need for a kind of qualitative assessment that goes alongside that quantitative estimation. And in particular, there needs to be an exploration about what causes that between study heterogeneity, because this has implications in terms of the robustness of that pooled estimate and its usefulness for decision making. So as I insinuated, there may be differences in terms of patients. This can include things such as the disease severity when they're recruited, medical history, so example, years since diagnosis of a particular condition. There can be differences in the study design, including when the follow-up points are measured, but it could also be differences heterogeneity due just to random chance. You know, these studies produce really quite different results. It can also be related to things such as the date in which it's conducted. You know, medical practice changes over time. You can get quite different results depending upon when the study has been developed. If we want to kind of go one step further in terms of exploring heterogeneity, we can look to, there are alternatives. We can look to either looking at subgroup analyses. So for example, it may be analyses based on disease severity of patients, or it may be based on particular timing of endpoints, or we can use a technique called meta-regression, which can help us to try and understand heterogeneity a little bit more, but also try and reflect that kind of quantitatively. And I'm going to go on to next a bit of rather brief detail on meta-regression, but just a kind of a little bit of a peek into what it means. So meta-regression is can be used to combine and contrast multiple sets of studies. So for example, we can look at studies subsetted by study design or individual measurement procedures. When we have determined that a single summary measure does not seem to either correct or sufficiently capture all of this clinical and methodological diversity in those subsets. So for example, we think that something is a particular driver of the treatment effect. We can use meta-regression to explore that. So this is, in essence, it's a random effects model with a study level covariate added. Okay, so it's an identifier for which study is being used to provide that treatment effect, and we can add this into the random effects. So it works very similarly to kind of standard linear regression, but the regression is weighted to take account of these different sizes of the individual studies. We can add in other study level covariates if we wish to do so. It quite simply extends to kind of multiple covariates. So that might be, for example, a particular measure of severity, particular characteristics of patients. Those can be added in to the random effects model. So this, I've just outputted here what the results of a meta-regression might look like. So here we explored the relationship between time delay to receive a PCI for heart attack patients and their 1 and 6 month mortality. Okay, so there was a kind of a priori belief that PCI related time delay drove outcomes in these patients. We had outcomes at 1 month and 6 months, so we wanted to explore those separately, and we wanted to see if whether or not having a delay to receiving a PCI had an impact on 1 month mortality. the kind of messages are quite difficult to kind of take from this. We haven't got many studies, particularly when we look at kind of 6-month mortality. There are fewer studies reporting at that time point, but we can see on the 1-month data there appears to be a kind of trend, a general trend, in terms of that we tend to get a higher rate of mortality when there's a longer delay. Okay, it's the difference between the treatment and comparator arm that's reported on the y-axis. So we tend to see that delay has an adverse impact on outcomes. And you can run this for different, as I said, different study level covariates. Here we've got the kind of mean estimate, and the kind of bands either side represent those confidence intervals as well. So thus far, we've been concerned with head-to-head trials for a single parameter. So this is kind of the next step forward, I guess, in terms of complexity. Now, it may be the case that the technologies of interest haven't been compared in a head-to-head trial, or it could be that there may be a head-to-head trial that exists, but additional evidence might be considered relevant as well. So drawing in evidence from alternative comparisons as well. And it's certainly the case in terms of health technology assessment, but also in terms of public health as well, that decisions can relate to multiple technologies, often greater than 2. And that can present problems for decision makers when they're only presented with these pairwise comparisons, A versus B. So those are the kind of limitations. So what do we do to try and provide a solution to that? So we can look to something called either indirect or mixed treatment comparisons. And these are a kind of generalization of meta-analysis methods that allows us to compare treatment arms, strategies that are not directly assessed within primary studies. Okay, so where we haven't got a trial that's comparing those particular interventions, it allows us to integrate this within one single framework, but crucially, it allows us to do that without breaking within study randomization. So what we don't just do is take all the effect estimates from one arm of the trial and all the effect estimates from the arm of another trial. We integrate these all within a single framework and don't break all of that very valuable information about within and between study differences. So here we've got an example where there is no head-to-head evidence on A versus B. So those are the comparisons of interest. So we haven't got a direct head-to-head trial, but what we do have are trials where treatment C is a common comparator. So we have A versus C and we have B versus C. Okay, so no trials, as you can see from the dashed line at this diagram at the bottom, no trials for A versus B, but we've got 2 trials for A versus C and 2 trials for B versus C. Okay, now we can use that in terms of a network of evidence to then determine what we might expect to observe had we conducted a trial that directly compared A versus B. So it follows that the treatment effect for A versus B is equal to the difference between the treatment effect for C versus B minus C versus A. Okay, and you can see that at the bottom of the diagram there. So basically you have this treatment effect and you minus the other treatment effect to determine the treatment effect that you might expect for A versus B. And I'll go on to some of the assumptions that are behind that, which are fairly strong assumptions, but it allows us to make some conclusions about what we may have expected in terms of relative treatment effects had that trial been conducted. Hopefully in the next slide, I'll put this into this will seem a little bit more real. So I've got an example here of 3 possible treatments. This is PTCA, alteplase, and streptokinase, 3 drugs that we're interested in knowing about their relative treatment effect. Here we have studies that allows us to calculate an odds ratio for PTCA versus streptokinase, and we have studies that allow us to calculate an odds ratio for alteplase versus streptokinase, okay? But crucially, we don't have it for that top two comparison, PTCA versus alteplase. And we want to use this kind of indirect comparison approach to come up with a treatment effect, had we observed it within a clinical study. So that's what we do. We do something very, very similar to what I just presented in the previous slide. The odds rate, so this is odds ratios, not a relative risk here. The odds ratio for PTCA versus alteplase can be calculated as 0.49 divided by 0.89, which gives us an odds ratio of 0.55. So had we conducted the study, we may expect the odds ratio to look something like this. Okay, we can also calculate confidence intervals, etc., for all of those things as well. So that's a kind of, I guess, a more simplistic version of an indirect treatment comparison. We can also go several steps further as well. So we can have a much more complicated set of comparators. So here we have got 6 different comparators. So this is moving to a network meta-analysis. Within these 6 different treatments, there are 15 possible pairwise comparisons here. So I've just presented the results here for 4 of those different pairwise comparisons. We can see here we've got odds ratios for some of those comparators, but we haven't got information across all of those pairwise comparisons. Now, we can put all of those bits of information together to inform a network of evidence. And this is what the network of evidence looks like. And it's the kind of starting point for a network meta-analysis, that we kind of draw out the representation for our evidence base. So we can see here the different comparators and the number of studies that we've got in each of those spaces. It also identifies where we haven't got those comparisons, but potentially have a bridging comparator, where it enables us to determine what might be the relative treatment effect had we observed that within a study. But it's much more complicated building on that kind of approach of a common comparator. Unfortunately, these network meta-analysis cannot be done in more kind of standard statistical software. They tend to be done using software such as Winbugs, which is freely downloadable, but it is a bit clunky. But there are lots of example files within there for anyone that's interested in conducting these type of analyses. Crucially, these approaches allows us to use a single coherent approach with multiple comparisons. So what we don't have to do is present decision makers with single pairwise comparators and say, look, if it's A versus B you're interested in, this is effective, this is cost effective. If it's B versus C you're interested in, this is effective, this is cost effective. It allows us to put it all together into one framework, and then we can also do things like calculate, as I've got in this table, the probability that that particular treatment will be the best option out of that entire set of options. It does it within one single framework. And it's very difficult to see how this can be achieved without the use of this mixed treatment comparisons. Again, it would be left for decision makers to try and join those dots themselves about, where they've seen a difference between A versus B, what that means for B versus C, etc., etc. Gets very, very complex when you end up with a large set of potential comparators and a large set of potential pairwise comparisons. So this provides that kind of unifying framework. Crucially, in terms of uncertainty from this network of evidence, it only represents uncertainty arising from sampling uncertainty in the contributing trials. Okay, the sampling uncertainty, for example, the confidence intervals, the standard errors that you determine from those individual studies. It doesn't represent uncertainty in those very fundamental assumptions that drive these types of analysis. So we can think of it as absolutely the kind of best case estimate of uncertainty. So it needs to be taken with a degree of caution because it has a limited way of expressing uncertainty. So in terms of assumptions that underlie that network meta-analysis, there are a number of assumptions beyond what we would expect for any meta-analysis, which is that they're all sufficiently similar, and therefore we have a rationale for pooling. There are particular assumptions that relate to network meta-analysis, and in particular, the assumption of transitivity. So that there are no systematic differences between the available comparisons other than the treatments being compared. Okay, if we feel that there are systematic differences, we cannot rely on those assumptions that allow us to compare comparisons where they've not been observed directly within primary studies. So as with any meta-analysis, those things are quite fundamental to determine before you think about how robust those resulting estimates are. So I'm going to talk very briefly now before I finish up on kind of, I guess, more kind of complex kind of extensions of meta-analysis. The first being meta-analysis using individual patient data. It's not often something that individuals have access to. But where they do have access to IPD, it is regarded as the kind of gold standard for meta-analyses. It does allow a lot more flexibility in the approaches. So it allows us to kind of adjust for individual study confounders, allows us to kind of minimize for heterogeneity. It offers a richness in the data. In essence, there is an approach to then synthesizing across that individual level data. So for example, you may have individual level data sets from two studies, and you still want to combine them because you still want a single measure of treatment effect. The first being that you can use a two-stage approach. So each individual study is analysed separately, and then you take those pooled estimates to combine it very much in the same way that we've talked about with the aggregate data. Obviously, you lose a degree of sensitivity there. So there is an alternative, which is the one-stage approach, and that would be a regression to estimate the effect size while stratifying by study. So you kind of combine that data. So yeah, two different approaches, each of which has kind of complexities, but yeah, there are greater possibilities if you have individual level data. So I've just got a quick example here of a meta-analysis of IPD. So this study looked at pooling patient data across randomized trials for endovascular thrombectomy compared to standard medical therapy in patients that had had an ischemic stroke. There was a large evidence base. This was 7 studies which pooled across over 1,700 patients with the primary outcome on functional outcome as the kind of primary outcome after stroke. The one-stage approach was used here, so that was that kind of regression analysis, taking each of those 7 studies, combining and having an individual level study identifier. So creates one giant data set, and I've put the link there for those that are interested in reading up a little bit more. You may be in the luxurious position of having 7 individual level data sets, but it doesn't often happen to most of us. So quickly on meta-analysis of non-RCT data. As I said, I've talked primarily about RCT data, which forms the kind of the pinnacle in terms of the evidence hierarchy that I presented at the beginning of this session. But you could be dealing with non-RCT data. Obviously, when we think about observational studies, we've got an increased risk of bias with that data, as we would have if we were dealing with it as an individual study. And we may have resulting bias in our estimate of treatment effects. But it may be preferred to RCTs in terms of the totality, the size of the evidence base, or potentially kind of generalizability. Those are kind of standard issues about observational data. Within a kind of meta-analysis framework, we can adjust the effect estimate for characteristics that may be related to the outcome or the intervention. So we're kind of here, we're looking at causal inference methods, and in particular, we can try and adjust for things usually we can't identify instrumental variables, which would be I guess, the preferred approach, but often in this context, propensity scores might be used to try and reflect those between study differences that we want to incorporate within observational data sets. And there are lots of examples of that. I apologize, I haven't put an example on this slide, but happy to follow up with any of those. Here I've just got an example meta-analysis of observational studies. You can see here much larger scale totality of evidence when we're looking at non-experimental evidence here. So lots more evidence to inform a pooled estimate. Here it uses a random effects model to do that as well. So finally, the thing I was just going to talk about was match-adjusted analysis. This could be an entire session in itself, so I really just have a very limited number of slides here on match-adjusted analysis. And that's really because it is something that quite often comes up, particularly in health technology assessment, particularly any folks that are kind of working on technology appraisal type topics. And match-adjusted analysis requires the use of individual level data, so we have got that caveat, and it attempts to match individuals based on baseline summary statistics that are reported from individual trials. So it works to try and re-weight patients in the trial by their odds of having been enrolled within the trials without IPD. Okay, so it's a form of propensity score weighting, but allows us to pool across studies, and we can do that where we have IPD, and we also want to pool with aggregate level data as well. And after matching, crucially, it allows us to compare outcomes across studies and assume that there is a degree of balance across trials. So helps us to kind of caveat where we haven't observed things within a randomized setting. There is lots of stuff written about match-adjusted analysis. It wasn't possible within this session, but I wanted to put one slide just to kind of highlight that this is also, another form of meta-analysis, which is really kind of being used quite a bit, particularly in HTA. So penultimate slide here on how to interpret the results. As with any interpretation of statistical analysis or quant analysis, as well as understanding the summary estimates that are being generated, there is a need to critique the evidence as well. And I think the starting point for that is to really understand the basis for synthesis. So, as I said, there is a strong basis in terms of informing decision making, but it's certainly the case that we want to understand the rationale for synthesis. So, is there a need to pool across all of these studies, or is it clear that an individual study really is the exemplar, the kind of gold standard, and informs the the particular decision problem of interest? So there needs to be a clear basis for the synthesis. And then also, if we form that basis for the synthesis, are the studies sufficiently similar for us to apply meta-analysis techniques to pool across that information? We also then, if there's a rationale for pooling them, we think they're sufficiently similar, we would want sufficient information on the methodology to determine the robustness of the estimates. So do the methods reflect the structure of the data, in particular this issue around heterogeneity? Do we believe that the trials are estimating one true treatment effect, which would imply a fixed effect model, or is heterogeneity likely to be an issue? And then, above all, have the methods been well described? Can we replicate those? Are there any biases in the results, and have these been recognised and controlled for? So very similar to, as I said, any critique of any quant analysis, we would apply those same principles to evidence synthesis. So my final slide is just kind of flashing up some of the key references in this context. There are quite a few things out there for folks interested in meta-analysis, starting with the kind of simple case of fixed and random effects and moving on to kind of more complex methods, and also moving on to where you may have opportunities for individual patient data as well. As I said at the beginning, the decision support unit has quite a few documents to help kind of support these types of analyses, and there are a number of specialist courses in this area as well. I would highlight in particular courses offered by colleagues at the University of Bristol who really, do very well in this kind of domain. I'm horrendously out of time, so I'm going to finish there and stop sharing my slides, hopefully.
Thank you so much, Laura, for a very informative presentation. So we've got few minutes left. If anyone has any question, please write it on the chat or put your hands up, and then we can answer some questions. Anyone?
I've stunned everyone into silence.
Yeah.
There's a lot of information. I'm absolutely aware of that. But I didn't want to stop at the kind of simple fixed and random effects. I at least wanted to give a flavour of some of the other kind of extensions to that, so that if folks read it in a paper, they have a kind of starting point to kind of delve further into it. But yeah, each of those individual topics could, you could spend a day talking about them in terms of the kind of technical exposition, but it's, a starting point, hopefully.
Yeah, and the recordings will be available anyway as well. So if they want to go back and have a listen again, that will be great. So I assume there's no more other question. No question. Just say thank you. So really great summary of evidence from Jessica. Yeah, and thank you. That's what she said. Thank you so much. Any more and from anyone? Got 3 minutes left. It's just completely silent. That's, I don't think there's more questions. So yeah, our recordings will be available in a few days, and I will send you an evaluation form. So we'll be grateful if you could fill up the evaluation form as well for a feedback form. Thank you so much, Laura.
Thank you. Thanks
Thank you,
everyone for listening.
everyone.
Thanks, Laura. Bye.
Thanks. Bye.